a postdoctoral researcher who is working with Professor Axel Hofmann at University of Illinois, Urbana-Champaign. And today I'm going to talk about a sub-micron wavelengths, the spin waves. So the magnon is a quantum of the spin waves, which is collective excitation in a magnetically ordered system. And if you think about, if you have a set of spins, and then if you align this along the magnetic field, and then if you excite this, and then if you can make the phase evolution of the magnetic moment along some specific spatial dimension like this, then they can form the spin waves. And in the thin-film geometry, there are well-known three branches of the spin waves. When magnetic field is applied along the thin-film direction, and then if the wavelength, a wave vector of the magnon is parallel to the magnetic field, then you will have backward volume magnetostatic waves, and which shows negative group velocity in the dipolar dominating region, and then show positive group velocity at the exchange dominating region. And when the wave vector is perpendicular to the film field, you will see magnetostatic surface wave, which is actually the surface wave whose amplitude is concentrated on one or the other surface. And when magnetic field is perpendicular to the film, you will see a forward volume magnetostatic waves, which is another volume wave, which show always positive group velocity. And another feature of the magnonics is magnon can interact with various other excitations and can be integrated into various other systems. For example, magnon can interact with phonons or the other magnons, or magnon can be integrated into 3D cavities or 2D cavities, and which also show some unique phenomena like dissipative coupling or spin wave non-reciprocity. And the magnon has been also proposed as a potential informational carrier. And to compare with the case of the phonon in the context of the quantum information, it has been demonstrated that propagating a phonon can mediate the quantum state transfer, and between two superconducting qubits like this. This is one qubit there, and there are another qubit there, and this quantum state in the two qubit was mediated through the propagating phonons. And in this case, phonons wavelength was about 1 micrometer, and its Q factor was about 3 times 10 to the 4. And I'll compare with this with magnonic case later. So my system consists of the ig film grown on the GGG substrate, and then on top of it, I grow antenna structure using titanium gold structure. And ig film was grown on the GGG substrate by magnetron sputtering and annealed at 800 degrees Celsius. And its saturation magnetization was about 1300 Ørsted, which is about 20% less than the typical reference value. So that means the crystal quality is not the best. And then on top of it, the sub-micron scale multi-element antenna were fabricated onto ig film by e-beam lithography. So they look like this. So the antenna have certain periodicity, and from this, if I apply microwave to this antenna, they will generate the time-varying Ørsted field, and this time-varying Ørsted field also have the same periodicity. And from this, I can excite a specific spin wave with a definite wavelength, which is the same with this periodicity. And this is our schematic figure of the antenna structure. So this is the multi-element part, and this multi-element part is integrated into bigger coplanar waveguide structure, and below it there is EEG film. And from this multi-element antenna part, the spin wave will be excited through these directions. And here is the overall measurement circuit. So I used a vector network analyzer. So vector network analyzer will apply microwave signal to this coplanar waveguide, and then they will analyze the reflected signal out of this antenna structure. And while I'm doing this, I can apply two different magnetic field. So if I apply magnetic field this way, I will make surface wave or Damon-Edgebach waves. Or if I apply magnetic field in this way, then it's parallel. So I will generate backward volume spin waves. And here is an example of the spectra I have. So in this case, I applied magnetic field along the Damon-Edgebach geometry, which means I applied magnetic field this way so that it's perpendicular to the wave vector of the spin waves. And the spectrum mainly consists of the two different resonances. The bigger, broader one corresponds to stationary Kittel mode FMR, which is non-propagating mode. And this smaller, narrow one corresponds to Damon-Edgebach or surface spin wave resonance with 1 micron wavelengths, whose line width is about 3.6 megahertz, which is very narrow one. And its corresponding Q factor is 1.7 times 10 to the 3. And if I convert this line width to in the magnetic field dimension, it was calculated to be about 1.2 Ørsted. So one may see which is very narrow line width. And associated total damping parameter was calculated by as 4 times 10 to the minus 4. And let me compare some line width from 3 different measurement settings. So these green one correspond to spin wave resonance excited from this multi-element antenna part, and which is you just saw. And then this red one correspond to the stationary Kittel mode FMR excited mainly from the other part of the coplanar waveguide. So red one is this, and this is the green one. And then finally, this blue one is coming from another setup, which is mainly coming from this centimeter scale bigger coplanar waveguide. And one feature is that the damping from this blue one is much larger than the other two. So I think because this is bigger, there may be larger the radiated damping contribution. And another feature is this green one. The spin wave resonance from the multi-element antenna have extremely small the inhomogeneous line broadening. So from that, I may indicate that my sample have some spatial inhomogeneity whose characteristic length is higher than 100 micron scale, so that within this small region, it was very homogeneous, but more than larger than this scale, it may be not that homogeneous. And this can be indicated from this comparing inhomogeneous line broadening. And here are the comparison between the data and the theory. So this is calculated dispersion relation of the Damon-Edgebach spin waves when magnetic field is perpendicular to the wave vector of the spin waves. And I fabricated several different multi-element antenna whose period is 1, 0.8, 0.6, 0.4, 0.3, and 0.2. And then I observed resonance signal except for 0.2 micron period antenna, and then they are presented here. So this is, for example, 1 micron, 0.8, 0.6, 0.4, and 0.3. And they generally are agreed well with the theoretical dispersion. And then for the other geometry, which is backward volume geometry, when magnetic field is parallel to the wave vector, I was able to get the data except 0.2 and 0.3. So, and here is the data, and they generally agree well. And then data also show this dispersion frequency minimum point also, which can host boson-Einstein condensation, for example. And so from these two comparison, I can say that this multi-element antenna operate as expected. So yeah, that's a good thing. And here is my general outlook. So I excited 1 micron wavelengths Damon-Eschbach spin waves, and it shows very narrow line width, which is 3.6 megahertz, and your Q factor was 1.7 times 10 to the 3. And I expect there is a room for improvement of factor of 5 if one use higher quality EEG, because when I measure the much higher quality EEG, which is commercial one, from this setup, the total damping was 5 times lower than this number. So that if I can make the same antenna from the best quality, I guess I can achieve maybe quality factor of the 5 times better than this. So, and in that case, maybe I can achieve quality factor up to 10 to the 4. And that, in that case, it is maybe possible to have application towards quantum information if I can achieve those kind of things. So this is the end of the talk, and thanks for your attention.
Thank you for the talk. Unfortunately, we don't have extra time for questions, but maybe we can meet you in the Gather Town after the session, like during the poster sessions. And we'll continue the session with the invited talk. Let me introduce the invited speaker. So the next talk will be, so next speaker will be Sajid Hussain, and the topic is magnetoelectric spin orbit memory concept and future challenges. Dr. Sajid Hussain